Good afternoon. I am Mr. Ish. You are joining me for this video here on Applied Derivatives Test, where we will look at 4 questions slightly difficult, going from easy to more hard, and they are not your ordinary style of questions, hence this will serve as a good test of our skills. And let's look at this first question. We have h of x. This h of x is a rational function which is made up of f of x, g of x in the numerator and f of x plus g of x in the denominator, and we have to find the derivative of this rational function. This type of question is hard simply because you got these letters in place of actual functions, and these letters can sometimes make you a little blind to those letters as you're doing them. Let's proceed with this question. When we're looking at this question, we have a quotient rule coming into play, but we have a product of functions in the numerator. We can just start with the quotient rule. Here's my g function, that entire numerator is my f function, and we can proceed with that. And let's do it. To make this type of question easier, eliminate all the x's. That way you have fewer letters to write. Like if we're looking over here at the rational function, and when we start doing it, we use the quotient rule, we'll do f plus g as our g function. We don't need to write these x's in there. It complicates things. It's times the derivative of the f function, which you know is fg. You have to do that minus the f function, which is in the numerator, times the derivative of that g function, f plus g. You see how it becomes so much easier when you've eliminated these x's. And this is going to be squared. This right here is a template of the quotient rule. You know you have a product rule coming right in here, product rule, and we'll do that. We have f plus g, and we'll do this. We'll open this up in terms of the product rule. You'll have g and the f derivative plus the f and the g derivative. You know the product rule. We don't need to spell this out 100% because we know how to do it. You would have done the g function times the product of the f function plus the f function times the product of the g function, and you would have gotten that. Minus fg times the derivative of f plus g would be this, f prime plus g prime, the individual derivatives of what you're seeing. And you see the primes over here represent the derivative is in place. What do we do over here? We'll open up the entire expression here in the numerator. You'll have like an a plus b times an a plus b, a sort of that type of factoring. You'll have to expand it out. When you expand it out in the numerator, you get fg, f prime. We'll be just saying prime instead of the word derivatives. Here you'll have, then you multiply with the next item, you'll have f square g prime. Then you'll do this g with these two items, you'll have g square f prime. And then you'll have g f g prime minus, expand this out, open it up, you'll have f g f prime minus f g g prime. All over what you're seeing here, f plus g whole square. You don't have to open this up. When you look at this, you can actually cancel things out. You have minus f g f prime and you have positive f g f prime. This cancels out with that. You have a minus f g g prime, and you can cancel out that with this right here, f g g prime, which is positive. What you have left with here in the numerator now is just an f square g prime, f square times the derivative of g, plus g function squared times the derivative of f, all over f plus g whole square. And this right here would be equal to the derivative of h of x, and that right here would be your answer. This next and second question is similar to what we've seen. After this, we'll change the question types a bit. Remember, we're going from easy to hard. Here you're seeing h of x is equal to this composite, but this composite is like a multiple effect composite. You can see there are multiple composites in there, and we have to find the derivative of this. Again, the fact that we have these f's and g's, which are not clear functions, but they represent a function, it makes the procedure difficult, and you have to end up just carrying this through with that difficulty. You know you have to use a chain rule over here, and you'll have to do several kinks of it, because we have a composite here. With regards to the sign, we have a composite with respect to the g, and then we have a composite with respect to the f. If u is equal to g sine 4x, then function with regards to u, well, you just have to say function with regards to u because you don't have a clear definition of f. If v is equal to sine 4x, right, then function with regards to v, you can just say g of v if you want. There's nothing wrong with you saying that, right? G of v. If w is equal to 4x, then function with regards to w is going to be what? Sine w? Makes sense, right? Let's play this through using the chain rule. And how would we do it? Derivative with respect to u, we have f of u, and then du over dv. We have g of v, right? Don't we? G of v. Then dv over dw. What do we have? We have sine w. The fact that you got these F's, G's and whatever, it just makes the application a little hard because you're not used to seeing things in this way. And then dw or dx, 4x. Now individually start running the things out. 4x is easy, I'll bring that out as a 4. Sine w is easy, I'll see that as a cosine w. At the end we can substitute for all of these. Derivative of g of v would be nothing more than g prime v, because this prime, as I've told you, represents that a derivative has been done of that original function. Derivative of f of u will be f prime u, and here the prime represents that we've done the derivative. Now we just plug in the items. We have 4 cosine 4x, because w was equal to 4x. Then we have g prime, v was what? Sine 4x, right? And then function f prime, right? We can leave the prime because we know we've done the derivative here, and the u will be all of this. G sine 4x, and this right here is the correct answer. You could have done this first and this second and this third and then that as a coefficient, but even in this order right here it's still fine. And you can see how these type of questions are slightly mentally more difficult because we're looking at unclear or ambiguous functions by these f's and g's. It just complicates it, but this answer here should be good. This question here is 2 parts, and I promise you will prove to be good. We have a volume of a right circular cone. You know the formula for a right circular cone is 1 over 3 pi r squared h. 1 over 3 times the pi value times the radius squared times the height component. Question A. Find the rate of change of this volume with respect to the height if the radius is kept constant. Question B. Find the rate of change of the volume with respect to radius if height is kept constant. Let's look at A first. It's not hard. Start with volume is equal to 1 over 3 pi r squared h. And what are we trying to determine? The rate of change of the volume. You know, for any given volume of a cone, if the radius were increased or the height was increased, you know the volume of that resulting cone will increase. You're finding the rate at which that volume component will increase. What is the rate of change of that volume if certain changes were made? And in each instance you're either changing the radius or the height. In this first instance over here, we're changing the height but we're keeping the radius constant. If you're trying to do a rate of change of all of this, how will we do it? This is derivative with respect to time, d or dt. Volume, you can use whatever designation, but as I open this up I'll use a proper designation and you'll see it. We're trying to find the rate of change of volume. So what we will do is dv, change in volume over change in time for that volume, is equal to, now you have to read this carefully, with respect to the height if radius is kept constant. We know 1 over 3 is a constant, pi is a constant, but now the radius is constant, so we can do 1 over 3 pi r squared. This right here is a constant or a coefficient which I have pushed outside of my derivative. Now I'm doing the height change with respect to time of this height component. You see that, right? This entire component has been pushed out as a coefficient. It does not really apply to the rate of change. It just serves as something which sits on the sidelines, but you bring it in at the very end. What's the derivative of anything like this? This is really v to the power of 1. When you do the derivative using the power rule and apply the power rule for the variables that are in play. The variables in part A are volume and height. So this becomes just dv over dt because the volume extinguished or it vanished by means of its derivative because a 1 came out of it. Anyhow, you have a 1 over 3 pi r squared. Again for height, what's the variable here? It's h to the power of 1. When you do this, you'll get 1h to the power of 0, which is just a 1, and you'll just be left with dh over dt, and that'll be it, right? So we will eliminate this 1 because it's accessory and it's kind of meaningless. What's our final answer here? What's the rate of change of the volume? The rate of change of the volume is this. 1 over 3 pi r squared times whatever the rate of change of the height component is. This right here is your final answer. If it looks ambiguous, it is ambiguous because you don't know what this value here is. But if you were given this value, you would plug it in right here because height is just a variable here to the power of 1. It would go away in the derivative component or the derivative procedure. You would plug in this value and you multiply with this, and that numerical value would be your change in volume over change in time provided radius is constant. So this here is the answer of part A. Let's look at part B. For part B, you don't have to do much erasing. You continue from right here. This right here is our general expression, but here we have to find the rate of change of this volume again. But this time the height is constant and the radius is not. So remodify everything. The derivative of the volume with respect to time, or dv or dt, is equal to 1 over 3 pi h. because now the height is constant and you have to find with respect to radius. The rate of change of the radius over time r square. You know, this is easy to handle. This here is easy to handle. Well, I've kind of already handled it. I did that already in the previous step. dv over v was just equal to dv over dt because this came out as a 1. Alright, we just have to calculate this, which is not hard. dv over dt is equal to 1 over 3 pi h. The derivative of r square would be 2r, because you're going to do r square, you'll bring the 2 over here and you reduce this by 1. You'll have a 2r to the power of 1, which is 2r, and then you know you still have dr over dt. And what we can do now is present this answer in a more suitable format with proper coefficients and constants combined. So the rate of change of the volume over time for this specific scenario B with regards to height constant and radius changing is 2 over 3. I'm just taking the 2 and the 3 together. Pi r h, rate of change of the radius over time. This is your answer. If you had a radius value, a height value, and you had the rate of change in that radius, you compute all of this, you'll have your change in the volume or change in time, and that answer right here would be good. So this right here is your answer to B. I already showed you previously the answer to A, and we're done with this question. This question here is our last question for this video, and I promise you it'll be a good and interesting question, slightly challenging as well. We have a volume of a cube that is changing at a rate of 10 millimeters cube per hour. How fast is the surface area increasing when the cube edge length is 30 millimeters? We're talking about volumes, we're talking about surface area over here. We know the volume of any cube, if you're using length as a dimension, is L cube, or length times width times height. But since we're talking about a cube, you know, square sides, all equal sides, we might as well say L times L times L, or L cube. The surface area for any cube, you know, you have 6 surfaces or 6 faces. Each face here has an area of L square, so it'll be 6L square. That's the surface area of a cube. We have this information at hand, so let's proceed with this. We're given the information with respect to volume and a certain length edge. We have to determine the surface area change. Start with what you know and go to what you don't know. We know the rate of change of the volume. What's the volume formula? Well, we put it down, L cube. We know there's a rate of change of this volume. If you were to do a rate of change formula over here, what are we getting? We're getting change in the volume over change in time, V, is equal to the change in the length over the change in time of that length. You'll say dl over dt, L cube. We've already established that this in terms of its derivative is just dv over dt because it came out as a 1. Derivative of L cube is no different than derivative of x cube, which would be 3x squared, or in this instance 3L squared, and then you have a dl over dt, right? We don't know what dl over dt is, but we certainly know this, and we certainly know that right at 30. And change in volume is that. So let's plug this in. We have 10 millimeters cube over hours. For the computations, we'll eliminate the units. dv over dt is this 10. And then we have a 3L square. We have the length edge is 30. And then that's a square is equal to dl over dt. We're right now determining the rate of change of this length, because this value can very well fall into this formula when the time comes. You take everything on the other side, you get 10 over 3 times 900. When you simplify this, keep it in a fractional form, you're getting 1 over, I've cancelled out 0 with 1 of that, I'm getting 1 over 270. That represents this dl over dt. So we've gotten that piece of information. Now let's look at this formula. Until now we were only doing this, now we're shifting to this formula. The surface area is equal to 6L square, and if you were to apply a rate of change on this formula, we would have let's say S, derivative or the rate of change of the surface area over time, right? Surface area is equal to the rate of change of the length or the edge as how they're using it, 6L square, all of that. But 6 is really a coefficient, you could have pushed it outside here. If I didn't, it's not a big deal. We have to find how fast is the surface area increasing. We know the length is changing, so the surface area is changing. If the length is increasing, the surface area must be increasing. We have to find this ds over dt. The derivative of this is no different than you looking at derivative of x to the 1, which will come out as a 1. Because by the power rule, this x to the 1 will vanish. You'll be left with just a 1. So you have ds over dt. 6 can come out. Derivative of L square is, well, a 2L. That 2 multiplies with the 6, well, you can just write it as 12L. and then dl over dt. But we have this dl over dt. It's right at 1 over 270. Let's plug this 1 over 270 right over here. 1 over 270. But we also have a length component. We still know it's 30. We'll erase this right here and we'll bring in a 30 times 30. There's nothing fancy I've done over here. I took this 6l squared and I did the derivative of l squared, which is a 2l. 2l times 6 is a 12l, right? 12l. L is a 30, so 12 times 30. So the rate of change of the surface area over time will be just this product divided by that. Let's do it. Is a 360 divided by 270. Since these numbers look very familiar over here in terms of what goes into it, we won't do a decimal answer, we'll do a fractional answer. 90 goes in 364 times, 90 goes in 273 times, so it's 4 over 3. But now let's bring the units. We're talking about millimeters, but we're talking about surface area, so it's millimeters square over time, which is hour. Here is your answer, 4 over 3 millimeters square over hour. So the rate of change of the surface area is 4 over 3 or 1.33 millimeters square over hour. It's a positive value, so you know that the surface area is increasing with time by this rate. And with that, we end this video. Hopefully this is a good, beneficial video for you all. Thank you for watching. Have a nice day.